We can now actually put multi-pixel time-of-flight cameras all over the body, and that, in some sense, extends tactile sensing beyond the skin. You can now sense things at a distance. If you're willing to put thermal cameras on your robot, it becomes much easier to detect people. This sort of weird-looking thing with the gray and the yellow fingers, those are actually human fingers approaching an inflatable robot. It auto-scales, so when the finger actually touches the inflatable robot, the contact area becomes very obvious, and everything else is dimmed. It turns out we just heard about magnetic field sensing. Electrical field sensing is very useful as well. I'm going to talk to you a little bit about radar. If we're interested in what materials things are made out of, spectrometers are fantastically useful, and the list goes on. And I would agree with you that some of those things on the list seem a little exotic, and how are we going to shrink them down and all this other stuff. But sooner or later, all these things are going to be attached to your phone, and it's the cell phone business which is driving sort of the development of small, cheap, exotic sensing. I do have to admit that I never thought I'd hear about putting bacteria on my robot as a sensor, so I'm gonna have to definitely think about that one. I want to clarify that many technologies have been used to measure skin deformation, and I'm actually talking about going beyond measuring skin deformation. So I'm sort of saying, I don't care how you measure skin deformation, I want to go beyond skin deformation. And the way I think about it is there's the what question, which is recognizing objects and materials and what can I do with an object. And there are where questions of where is it, how is it oriented, what's its shape. And I sort of think about this whole suite of sensing. There are some sensors like sound, vibration, ultrasound resistance, where you really need to be in contact with something to measure it. And there are some sensors that do best when you're actually not in contact, the various cameras we talked about. And then there are many possible ways you can sense things where you're nearby or you're touching, and typically these are active sensors, and you get some sort of response, and that's very useful. Often, for example, identifying the materials that something's made of. And Carmel showed the opportunity to put materials or sensors on objects rather than on robots. And that opens up, for example, transmissive sensing, where you're actually sensing through an object, which is very useful for a lot of sensing. I started out asking the question, how can we optically do tactile sensing? But we also made the skin transparent, so the same cameras can look through the skin and see what's going on. My Akihiko Yamaguchi did basically all the work and has, since going back to Japan, has developed a number of these systems. We call it finger vision. And the most useful thing about finger vision is this business that you can actually basically react to things and visually servo. And I view this as sort of extended tactile sensing. But this kind of thing is potentially actually more useful than tactile sensing. In the last few talks, we saw a lot of soft hands, which to some extent, I think some of them were just grasping things open loop. That's the beauty of soft hands. And the issue, I think Antonio mentioned, you got to get the hand in the right place. Well, one way to get the hand in the right place is to use a vision system that's on the hand, so you're directly measuring the offset between the hand and an object, rather than trying to, for example, do it with eyeballs in your head and essentially subtracting two big numbers, where's my hand, where's the object, to try to estimate a much smaller number, which is actually not a good way to do it. This is just showing finger vision and the image quality, and it's not very good. But it's good enough to very sensitively measure slip, and it actually, this system, the vision can measure sort of very small forces that you'd have to have a very, very soft elastomer to see a displacement. I think these displacements are very small, and often it's the image of the object that we're reacting to, rather than you can see we're tracking markers. Okay, let me jump ahead here. So what did we learn from all this? Is that seeing things nearby might be actually more useful than tactile sensing for a robot. We get very low force control, detecting slip. One of the big problems for robots is after you've grasped something and put it somewhere, getting your fingers off of it is difficult, particularly with soft hands, because it's sort of like a micro scale jamming effect. You squish the hand into something, and when you pull it away, typically there's adhesion, and you pull whatever object it was that you just put there either away from where it was supposed to be, or more often you just knock it over by trying to release it. There is a downside to trying to turn your skin into windows, and that is like the windshield of your car, it gets dust and dirt on it, soft elastomers get scratches, wear and tear, and if you have a soft lens, typically you distort the image. So this next project was to try to do something very similar, but in this case, we're switching to rigid lenses and separate cameras, and it's much easier to keep a rigid lens clean. You can wipe the soft lenses, but once it starts to get scratched or sort of roughened, the optical quality is quite degraded. So here in this case, we took a gel sight, and next to it, we put two different cameras. One's a RGB camera and the other's a time of flight camera. The time of flight camera is useful if, for example, there aren't a lot of visual features to look at. You can still get a decent depth image. And the idea is, what can we do with these co-located cameras that would help tactile sensing or help the gel sight? And in the top row, you see what the RGB camera sees, and yes, we can register a CAD model to that. And the gel sight might see this image. I have to say, the gel sight, what the gel sight measures is, from my point of view, unbelievable, beautiful, beautiful pictures. So in this case, we humans can tell we're on the button, but it was very useful for the robot that you were tracking the object all the way down and predicting you're going to land on the button. And indeed, on a CAD model, it's able to say, we landed on the button. In the bottom row, we took something with repetitive features. This is a box cutter, and you can lock the blade in a variety of positions. So that what the tactile sensor sees is this repetitive texture, and it had, the tactile image alone isn't enough to figure out where you're touching the object. If we have this prior of where we're likely to hit the object, we can actually resolve a lot of this ambiguity and figure out which tooth we are actually on. So here what we did is we replaced the soft transparent material with rigid lenses. We again saw that vision provides very useful priors. There's been a long literature about optical flow and sort of a Gibsonian talk about affordances and the environment tells you what to do. What we discovered is, well, yeah, you can measure optical flow and use it to predict contact location, but because there's sideways movement of the camera, you really have to make a substantial movement, about 10 centimeters, to reliably predict where the center of expansion is. And as I said, we were able to resolve ambiguous contacts, and also if there is no tactile texture, the vision system is all you've got. I've been recently interested in radar because I want to basically find ways to see through things. I was very inspired by the comic books as a child, and in the back of the comic book, there was always an advertisement for X-ray glasses. We're not there yet with X-ray, but to some extent with radar, we can see through things. What's driving radar is that there are now these radar chips where everything, including the antenna, is on chip. The other thing that's happening is we're going to much higher frequencies, so we have good spatial resolution. So for example, I've tried putting on 60 gigahertz pulse radar. That probably corresponds to what you traditionally think radar does, where it sends out a pulse and waits for the echo. It's kind of like sonar, except everything is happening at the speed of light. Another system we're looking at is even higher frequencies. We're almost at terahertz frequencies, which are these frequencies are what are used in the airport scanners. And you remember the controversy of it looked like people were, the operators could see people naked because essentially these systems see through cloth very easily. And that's actually the kind of thing we're trying to get robots to be able to do. Another interesting system is what happens if you have many antennas and you can select which antennas you're actually using. This is called multiple input, multiple output radar, and it's a beginning step towards forming images rather than single beams. So you can look, this thing on the right is, you can think of it as a very low resolution camera. So far, the pulse radar has been easiest to use, and we're very accurately tracking targets that are in front of the robot. Of course, with radar, you need something conductive, but actually, if you are dealing with a plane and the radar is shooting straight at it, pretty much everything gives you a return because it's conductive enough. Obviously, you can set things up so that things give you very good returns, sort of off the shelf. Metal cans do very well. With boxes, you can put a little foil tape inside a corner that creates a retroreflector. So you can think of this as sort of like a barcode we can put on anything. We can also put a retroreflector on anything. We can see through cardboard and plastic boxes. Radar, because it's not forming images, but it's instead finding distances, the way you get a radar image is you sweep the radar over something, and basically, depending on your pattern of motion, you can emphasize some features over others. And what that means is that robots and radar are made for each other. If you put the radar on the end of the robot can actively move it around to do a better job perceiving the environment. With vision, we want to avoid specularities. With radar, we want to maximize specularities because that's when you get a good measurement. The thing we want to look at next is putting ultrasound sensors on the tips of fingers so that when robots are manipulating people, you can track the internal tissues and try to minimize pain or tissue damage while you're trying to manipulate someone. So there are going to be coming out three-dimensional ultrasound chips. Current transducers are basically just give you a 2D scan. They're a line of transducers. The 3D thing gives you a plane of transducers. And by choosing which transducers you use, you can actually recover a 3D volume without moving the sensor. Okay, so the point of this talk was to say, maybe to make the great leap forward that we've always wanted to make in terms of manipulation, we have to go beyond thinking that our sensor measures skin deformation. Okay, let me stop there and relinquish control, and I will take any questions.
Thank you very much.
Very much. So we have some question. Inchi, please.
Hello, can you hear me?
Yes.
I hear you.
Okay, good. Thank you very much for that wonderful talk. And I wanted to know, because this kind of sensors are really great for robotics, and I really agree with you. However, if we, for example, think to integrate them into prosthetics in order to give back touch sense to amputees, or for example, for interfaces for people that are isolated into hospital rooms, like, would you think that it can mimic also this sense of touch?
I think is still an open question. What's the best way to present information to people? On the one hand, there are these studies that basically say the brain is incredibly adaptive. Whatever information you provide, sooner or later the subject figures how to make use of it. On the other hand, there are plenty of studies that say if you provide feedback that somehow is natural in some sense, people basically learn it much more quickly and may achieve higher performance with it. So it's an open question. A third issue is, do you want your prosthetic, for example, if it's above knee prosthetic, do you want it to somehow control itself? Or does the wearer want to feel that they have control? And there's a lot of evidence that attempts to do fancy things with the control of a knee in an above knee prosthetic typically don't get good acceptance from the users. The users want to have a very predictable behavior in their system, so they prefer a basically stupid knee to a smart knee because they can figure it out. So, you know, we would sort of have to ask these questions on a case-by-case basis.
Right.
So, if I may, I wasn't really talking about making limbs more intelligent, but more because there are a lot of studies that involves this touch mechanisms into mental health, and that it is important to feel whatever is surrounding us in order to maintain this mental health. So it was more about that. Also, like, if you think like we can also learn about with new information that how we can touch also the world. So yeah, actually it's good perspective, but not about making them more intelligent. Like, yeah, no one wants a limb that acts alone.
So there are as I understand it, a completely separate touch system that's being referred to as the effective touch system, which seems to be about what you said, people socially relating to other people, mothers with babies, things like that. It's an open debate whether we would want robots with effective touch systems. We could implement similar things, in a lot of different ways using a lot of different sensors. With people, I think it's absolutely true that touch plays an incredibly important role in our social interactions and in our happiness. That's one of the things we found out in the pandemic. And, I'm oriented towards what are we going to do about robots? I don't want to take away anything from people.
I think we have two more questions, Chris. Prajwal.
Thank you. Regarding the proposal that you had mentioned in the beginning of your talk about spreading eyeballs all over the robot, how would one tackle the information flood in that case? Like, there would be so much information and the computational load, and how would one tackle that?
Well, you could ask the same question about our somatosensory system. We've got, sensing all over the body. How do we make sense of it? It's even worse because in the somatosensory system, you got to pay attention to, the pose of your body, how your body's moving. With cameras, you could sort of make sense of what's coming out of a camera independent of where the camera is. And the amazing thing about humans is their attentional system. I'm wearing clothes all the time, or except when I'm not, and I don't feel them, except when something unusual happens. And if you sort of lean back in your chair and ask the question, well, what kind of system could do that? The system has to be able to predict what, well, normal clothes feel like and say, oh, nothing unusual is happening. And it has to figure out, oh, I got a rip in something, or, my belt's loose or whatever. That's an incredible system. It's able to predict what the measurements should be. And if you can do that, then you can manage the information flow, because all the stuff that's not a surprise, you can ignore, which is how your system works anyway.
Topo, can you ask your question during the panel discussion, because we are 10 minutes behind?
Fine.